we make a lot of different things that get used in a vapor compression refrigeration cycle. How many of you know the difference between a British thermal unit and British racing green? Nobody? Oh, one. Yeah, wow, one, that's it. Ragu, this is going to be, we need to back down to cat, dog, red, blue, the primary colors and how to count to 10 without taking off your shoes. That's where so I need to not use big words like adiabatic or deposition and sublimation and such, because I'll be, okay. Refrigeration as a basis. Before there was mechanical refrigeration, I've scounded with some of these off the internet. Actually, that's an old photograph. There's two of my brothers in here harvesting ice when the river froze over. But rivers and ponds and streams and lakes would freeze over in the wintertime. Pretty common occurrence. And for eons, this would get harvested and then transported by, for those of you who don't know, those are horses, and a wagon. That we used to use those for transport. The Amish still do. They might know something we don't.
They used to use ice houses too.
And they used to use ice houses as well. And they might still do. And for those of you who have ever called the refrigerator in your kitchen or heard your parents call it an ice box. Yes? Anybody? No? If you've heard that thing called an ice box, it was because it was an ice box. It was like an old style Yeti cooler. And if you want to see one, how am I doing on time, Ragu? Am I going to have to speed up a little bit already?
Yeah.
No. See you watching your clock there, just making sure you're okay. If you want to see one that's been repurposed, go over to the old Dutch. The credenza there at their registration desk is an old ice box. Oh, what do we got there? What's going on? I think this wind or I don't know anything about that. Can I get rid of that? Nope. It's I can probably dismiss it. Are you sure you want to dismiss? Yes, I do. So there we go. How's that? The ice would get delivered from an ice house, unless they had harvested and they were just storing it in sawdust and straw in caverns or quarries or wherever they could do that. I know my mom grew up on a dairy farm, and I can't touch this stuff, by the way. And they would milk the cows twice a day by hand, and they would drink whatever milk they wanted. The rest of it they'd make into butter and cream, and they'd sell it. It'd be sour cream because it had gone bad. That's my argument about why all dairy products aren't good for you anyway. And someone would come by and pay them money for that. The milk they didn't drink, they used to feed the hogs because they couldn't keep it long, because they had maybe a 58 or 60 degree cellar underneath the house because they didn't have a refrigerator. Actually, they didn't have any electricity at all for the longest time. You had to go outside and use the toilet. I still do that sometimes when I can't make it. Now, initially being in the business, I heard the context of a unit of weight because I already knew what 2,000 pounds was, because I had some ants that were damn near that big. 2,000 pounds was a ton, right? That's what, how do you correlate that back to the capacity of, my first exposure was to an air conditioning unit. We were at the time putting air conditioning equipment in residences at a rapid pace because nobody had it unless you were extremely wealthy. So this shows you the correlation between that unit of mass and the capacity of a unit. It has to do with taking a 1-ton block of ice and melting it over the course of time, 24 hours, and the amount of energy that's dissipated, the cooling effect that is exhibited by that is what is the source of that terminology. How many of you knew that before coming in here? How many of you didn't know that before coming in here just now? That's okay if you. That's what we want to do. We want to educate you on that basic stuff. And we still use that today because it was on the basis of using ice, which we still do. Anytime you go to the lake or on a picnic and you put ice into a cooler, you're taking advantage of that. Now, grocery stores are a key part of our business, and they're essential for us to be able to eat well. throughout the course of the year, stay healthy and all that. Now, I don't know how accurate that is anymore to say that there's 50,000 stores. I mean, John here might know better than I do, you know,
That's
or
about
Matt.
right, Jim. That's
Is
about
that
right.
about right? Lots of new construction going on, and certainly as typified by the calls that our S3C tech support people take, Walmart's doing a remodel or a build daily, it seems, because we're inundated with calls on what's going on. Why doesn't my case get cold? Why isn't the unit running? Why is it defrost too short? And so on and so on. And if we don't have all of that in place properly, there's lots of lost money, which follow the money. Now, there are a lot of supermarket chains. Some of these are people you know and customers you know, and they're a critical part of our business. And over the past, we've enjoyed some success because we've helped to encourage the people that work at these places and facilities to specify our stuff, which then in turn means the equipment manufacturer, who's predominantly going to be the one that buys it from us, is constrained to buy what the supermarket chain asked them to buy. And sometimes that works out well. And there's a lot of stuff going on here right now. We've got, here's Phil Phoenix, Hussman, Zero Zone, and others that build equipment that utilize our products in supermarket and refrigeration environments. There are some, whoops, how did that happen? I think he's got this thing, timing thing to keep me on track. Some of them, like in the case of True Manufacturing, which are in our backyard, have decided to utilize a certain refrigerant that's kind of unique that we'll talk about before we finish up for today. Now, what's happened in business trends? Some things have changed with the pandemic that came along and resulted in a broken leg for me because I jumped out of a second floor apartment bedroom window because the husband came home early. You got online ordering going on, curbside delivery, home delivery, and so on. And if you weren't ordering online before, you probably are now. Right? How many people have started doing that? There's even services, I understand, that will take your order online, bring it out to your home. If you give them the door code, they'll bring it into your house, put it in your refrigerator or in your cupboards. Ooh, wow, I don't want them coming in my house. In-store restaurants and bars. There's Whole Foods down in Austin, Texas, where you can sit down at a restaurant, order food, hire somebody to do your shopping and sit there and drink the whole time if you want. And reusable packaging and containers. Some of you remember a time, looks like food's showing up. Nope, that's water delivery. Are you doing ice delivery too, Ragu, or just water these days? Okay. There was a time where soda and beer were in reusable bottles that were made of glass that we recycled. You had to pay a deposit. You got that back. So there were kids that would go around the countryside looking for glass bottles to take back to get, what it was, 2 cents a bottle or whatever. Some of that in some communities is experiencing a resurgence as an overall environmental thing to keep things in check. Now, this is something this is near and dear to me here when we look at workforce trends. I'm just going to jump right into that because I had family that was in this business for decades. And my father taught how to braze and weld at the pipe fitters apprenticeship program. And we taught a lot of people that are doing a lot of work currently, even up in our area. And those older folks have retired, or in actuality, in the case of my family, left the planet already. And there's a lot of people that are doing that. And our need for educated people, which is something what we're kicking off here, Ragu, thank you for instigating that because I think it's valuable. There is a need to educate people at the basic level to help encourage them to go on further because we need them probably more now than ever. And there's going to be that because of the Environmental Protection Agency in this country and other reasons, which John Woodhouse can elaborate for hours. And he does that oftentimes when I invite him to specialist class. He can tell us what's going on with those trends, and the need for lower global warming potential refrigerants is being legislated, and it's going to happen whether we like it or not. Things that kicked that off back in the 1980s with refrigerants that were intended to be long life and long, the end all and be all, are now we found aren't. And we have to come up with new ways to accomplish things. Stores, which was the mega store for a good long period, are now going back to smaller stores. And we're seeing the use of more electronically controlled devices all the time. One other thing that I just mentioned here, it would be worth your while to research on your own to learn about it. And Jason Forshe's written a nice little paper on it that you can get off online. Is the annual walk-in energy factor thing, AWEF. It's legislating how we design high-side equipment and a lot of the other, and how we select components to make the systems work for walk-in coolers and freezers if they're below a certain size. And that impacts a lot of things, including how our devices work. It's just one more legislative action that's being taken. And you can research that more. I just wanted to let you know that that is out there. Supermarket of the future, how is it going to look? By the way, you said this is being recorded? Well, we already did. Because this is part of our webinar. Most all the slides you're going to see that I'm going to present, I've done before. And it's in supermarkets of the future. It's on our YouTube site. So go to Sporland Video. I think that's all one word. You can find a wealth of information. I encourage the younger engineers here to spend some time out there. And it's not all created by me. Lots of help along the way. Dennis Setchfield back there has helped us put a lot of this together. Marketing communications helps. We repurpose a lot of slides. I can't take credit for generating these. I can take credit for livening them up a little bit, but I can't take credit for that. But increased efficiency, fewer refrigerant leaks. I always contended if we'd have focused on fixing the leaks and training technicians, we wouldn't have needed to get rid of R22. But I got that. New low GWP refrigerants are going to happen. We might start seeing more propane. That's not the same stuff you have in your barbecue grill, because that's not really propane. That's a whole bunch of waste gases that get burned to create a flame, and heat so that you can cook meat. But refrigerant grade propane, you're going to see more of that, I think, and might even start seeing CO2 being used as a refrigerant. But we're going to get into more of that. Wow. Does that look complicated? Do you even know what that is? John. I'm not asking you. And what the hell are you doing in this class anyway? I don't know.
Okay, I'll shut up.
Yeah. Multiplex refrigeration system. It's DX because it uses something called direct expansion. While that looks super complicated, you're going to learn real shortly that every vapor compression refrigeration cycle only has 4 main components. Whether it's that little refrigerator we got back in the training room, or the one you might have in your kitchen at home, the system in your car to create air conditioning, or the unit in your home, or what Schnucks and Deerbergs and everybody else in Walmart have in their systems. 4 main components. And if you don't know what they are, I'm going to tell you. One is the compressor. Some people call that the heart of the system. It helps to create the high and the low pressure sides so that we can see a phase change in the refrigerant that flows through it. That's that magic stuff that some people like to call Freon, which is kind of like, Kleenex, Crescent Wrench. It's a trade name. I got that right, didn't I, John? Freon's a trade name, right? Yeah.
Indeed.
And some people call it gas, which lends the connotation that you're going to use it up. It's refrigerant. That's the stuff circulating through the system. And this helps to create that high and low side so that we can reject heat through the condenser to the ambient, or to maybe someplace where you could reuse it. And then you've got an expansion device over here that works in conjunction with the compressor to reduce the pressure and then introduce it into the evaporator, and the magic stuff happens there. Why do I say that? How many of you ever put a tea kettle on the stove to boil water? Yeah, come on. You guys did? So how do you get the water to boil? You add heat to it. Energy. If you think of it as energy, it's transfer of energy. This is, John, are you going to sleep on me? It looks like you're closing your eyes. I'm boring the hell out of you. No. I'll bring a blanket next time if you want.
Issue with that, but
No. Here in the evaporator, we're introducing a refrigerant that we want to boil. And when we boil it, it transfers heat. It's transferring heat from whatever it is that we want to cool, chill, freeze. It's like that teapot on top of the stove. We boil the refrigerant. It turns into a vapor. We send it back to the compressor. The compressor elevates the pressure, and we start this all over again and keep going and going and going. Every system has these components, even the CO2 systems we're going to talk about, most of them. Anyway. Now, oh, wow. Pressure enthalpy diagram. John dreams about these in his sleep because he just loves it. And he does that instead of watching movies and stuff. How am I doing on the time? I'm doing all right. Not so much. Yeah. This is a depiction of the thermal physical properties of a refrigerant. The refrigerant manufacturers create these diagrams. This is just an oversimplified view of it. It shows how the refrigerant changes state as the different conditions occur. And if I superimpose the vapor compression cycle on top of it, you can kind of see what state of matter the refrigerant occupies as it circulates through that system, whether it's superheated vapor or it's liquid or it's a mixture of both. And there, again, is those four main components. No matter how complicated the system is, if it's vapor compression, which is the majority of the equipment we deal with. Now, it's not the only way to create a refrigeration effect or a cooling effect. Before coming here, I sold something called an absorption chiller. It doesn't have a compressor. In an attempt to help keep the global warming under control, if you believe all that stuff, and I'm not sure, John, you and I have talked about that at length, so we're not completely convinced that that's real, but anyway, we're not going to go down that path. There are different ways to do it. And this is one depiction of a so-called glycol system where there is a refrigeration plant that's over here that could be vapor compression, just like we've already talked about. But the stuff that gets circulated through the store are to the load of the cases or to whatever we're trying to cool or chill or freeze, not so much freeze. In this case, there's an intermediate heat exchanger referred to as a cascade evaporator condenser. And that terminology is completely correct. It's not, but it's just meant to be illustrative. But it's an intermediate heat exchanger. I think generically I can get away with that. And we're circulating a fluid that could be water in an antifreeze preventative measure and send that to the caseload where we would cool or freeze things. This is essentially what I would call a chilled water loop that you'd see in air conditioning in a campus environment, done to this day. Some supermarkets latched onto this as a way to reduce the refrigerant load because they're getting penalized or being scrutinized by how much refrigerant they have on site, especially if they have leaks that they have to fix and they're buying tons of more refrigerant. Boy, did you hear that? Slip tons in there. But there is a penalty to pay for this because of the energy loss that you encounter with that heat transfer effect. Now, these kind of fell out of vogue for a while. I think there's maybe a little bit of momentum picking back up with this. And I only show this to you because these are out there. And now one good thing about it is we can take this heat transfer surface here and we can pretty much fill it full. We don't get the loss of a DX system. I'll talk a little bit about it. So this is, as we go to the next step where I'm going to talk more about systems that use a more traditional refrigerant, or CO2 for that matter. Here are some desirable qualities that we might look for any given refrigerant or substance that we're going to use to create this cooling effect. Now, back when I got started in this, it got hammered into me here at Sporlan that we only want two things circulating through a refrigerant system or refrigeration system. Anybody want to guess what they are? I've used the terms of one of them just over and over and over again. What are we talking about here? Well, refrigerant. That you got to circulate refrigerant through the system. Some type of heat transfer substance. And in the case of these vapor compression cycles, it's something that will change phase at the points where we have the desire to cool. What's the other one? A lubricant. I didn't even let you answer. A lubricant. We need that lubricant because there's a lot of heat generated by that compressor doing work. And we need the lubricant to help with that. In a lot of instances, that lubricant goes on for a ride out through the system. And we've got to do things to help control that. But these are desirable qualities that one would originally consider for a refrigerant. There are things like high latent heat that gets into that phase change thing. A low boiling point so that we can achieve that cooling effect. You know, we're going to boil it at the temperature that we want to create. Not 212 degrees Fahrenheit with water at atmospheric conditions, but maybe 40 degrees Fahrenheit that we could use to cool a house, or maybe even lower if we want to make cold beverages or maintain food products, or even freeze things like ice cream, which I can't eat, by the way, which is really shits. Low specific volume. Oh, here's one that really jumps out at me. I think it's really interesting. High critical temperature. I'll talk about that more. Remember that one. High critical temperature. It's nice if it's non-corrosive and stable. Oh, I'll jump down. No affinity for constituents in the atmosphere, because we don't want to deplete ozone or create global warming concerns, right? But how about non-flammable, non-explosive? That wouldn't rule out anything, would it? How about inoffensive odor, non-toxic? Same there. Low cost. This came out of a book that's, John, you're going to sleep again. Didn't wake up. No, as you just was kind of.
I already know it. I can nap during the sleep.
Oh, okay, fair enough. Household Refrigeration by H.B. Hull, 1926. Over almost 100 years ago. I mean, these things sound like modern design requirements. They haven't changed. Not really. Now, history. What sort of things did we use as a refrigerant when we first developed vapor compression cycles? Well, there might be some stuff on here you've heard before. There might be some stuff you haven't. Sulfur dioxide. Probably don't know about that. Ammonia. That's been used as a refrigerant for almost ever and continues to be now. Might be a little toxic. Remember that non-toxic entry on the previous slide? Methyl and ethyl chloride. So those are probably gone away. We don't see those much anymore. Oh, wait a minute. Butane, isobutane, and propane. Those were used early on. But guess what? They're only slightly flammable, right? Right, John? What is it you tell me all the time? If I want to be a billionaire, come up with a way to make propane non-flammable as an additive?
Yeah.
I'm working on that. Carbon dioxide. That might be. Raghu, what's carbon dioxide?
Something that can be out.
Oh, okay, fair enough.
Like,
Nitrous oxide, air and water vapor. If you get the pressure of water down to the right point, you can use it as a refrigerant. And there's other things, but there's problems associated with all those. That's why some brilliant engineer chemists came up with the chlorinated fluorocarbons in the 1930s and made most of these obsolete. But that little chlorine molecule did dirty deeds up in the upper atmosphere, and we had to go down a different path. Guess what? Now we're starting to look at propane and carbon dioxide and other things again. How interesting. Now, why CO2? And John, I'm not trying to take away any of the things that you're going to talk about. This is at a high level. If you use CO2 in a system, and one of the things I think that our customers are interested in this, they are frustrated because they'll design or install a new system with a refrigerant that they think they're going to get to use for an extended period of time. And there'll be legislation coming in place that gets promoted by the EPA.
Your slide is why CO2, John's why CO2 now.
Okay. Fair enough. I had something real profound I was going to say, and I'm having second thoughts on it because I got my own acronym for the EPA, and I'll probably get in trouble if I use it. It's not Environmental Protection Agency, but you can ask me later, and I'll tell you what I said here. Something about eco-terrorism. refrigerant reduction. If you reduce or eliminate the CFC, the HCFC, or the HFC, or the HFO, maybe you have something that you can deem as retrofit proof. And I think the Aldis of the world, which we've got one here in town, that's using CO2 as a refrigerant, they are trying to set themselves up in a position. They say it's because they're concerned about the environment. I think that may very well be true, but they're also concerned about the money they have to spend on retrofitting equipment. And they're frustrated with it. So some of these companies, manufacturers, are going down that path for that reason. In the case of CO2, you can have pretty decent performance in the system, and you can install smaller piping. You can do things like have better energy consumption if you compare it to that glycol overfeed pumped liquid system I showed you. But there's penalty to pay with this. You know, these systems can be a little expensive to install. They can be a little expensive to operate. And there's some unique problems that come along with it, especially the transcritical systems, which we'll talk about here soon, and I'll let you know what that means. We're going to discuss on a real high level liquid overfeed, Cascade, and transcritical CO2. Liquid overfeed and the Cascade are subcritical. Now you're saying, what the hell does any of that mean? Subcritical, transcritical? I'll explain. But something that's interesting to note off here to the side, I've got temperature versus pressure at different conditions. And what's interesting with CO2 is the pressures involved with it. Over here, minus 20 degrees Fahrenheit, that's fairly cold, right? I mean, if you're in a minus 20 degree room, you're freezing your backside off, right? And Dennis is going to put even more than that shirt jack on. He might even be wearing a hat. All right, at minus 20 degree Fahrenheit. What pressure is associated with that? 200 psig. John, is that fairly high for that temperature?
Fairly high.
I mean, that's almost getting into R410A range on the high side. Almost, not quite. And then if we take temperatures up, let's look at plus 20 degrees. What's the pressure over there? I think my eyes are going bad on me. I think that says 407. Man, that's getting up there. Now, what happens when the CO2 gets up to like room temperature? I'll leave you guessing for a minute, but I'll tell you here quickly. Oh, looky there. Already, that slide's a little discombobulated, I think, because it doesn't like your computer or the template that you put it on, Raggy. So that's why it's completely your fault. Remember the pH diagram? A depiction of the thermophysical details or data of a particular substance that could be used as a refrigerant. Now, I may not have that accurately, down to the thermodynamics level of the description that I just gave, but it is a collection of a lot of information that's put into a graphical form. Usually, if we're going to use things for calculations anymore in the modern era, it's in the form of a computer program like refrigeration properties, RefProp, where we can draw data from it. We don't rely on a chart or a graph. But when I was younger and you had to use your fingers and toes to count a slide rule, you had charts and graphs, and you relied on stuff like this immensely. And anything that plots over in this area is vapor. Over here would be a liquid. And anything underneath this dome is a mixture of the two. In fact, this dome that you see is sometimes referred to as the liquid vapor dome. It's this saturated condition. So if something's liquid, everybody kind of has a feel for what liquid means, right? As you reach this point, you're right at the transition where the liquid goes from being all liquid to liquid and some vapor. And as you move your way over here, you get to the other transition point where you start becoming all vapor or gas, if you will. Now, the critical trans and sub that comes into play has to do with this point right here. Right up here at the apex, that gets called the critical point. Up above the critical point, stuff is in some kind of weird realm, almost like multiverse thing of sorts. And substances don't like to behave the way we want them to. If it's superheated gas, it doesn't want to condense. And along with that comes some unique problems if we use a substance that's going to encounter that, or where we're going to encounter that in the system. And that's exactly what happens with CO2. Because at 87.9 degrees Fahrenheit, as opposed to the 75 degrees Fahrenheit that the Danfoss guy says on that YouTube video, we reach the critical point, and the pressure of CO2 is 1,070 psi. That's a lot. Or in the most technical term that I can say, that's a shit ton of pressure. And a lot of things can happen at that point. And anything that would plot above that is considered above critical. Makes sense, right? The fancy word that comes along with that is transcritical. And some people will utilize that, especially in systems where that CO2 might, as it goes through the system, be in periods where it would plot above the critical point or below the critical point. So it's transported back and forth across that. If everything happens below that, guess what? It's below critical, subcritical. Don't let those terms cause you distress. I even sometimes make fun of it, and I say, have you ever heard, John, have you ever heard this one? You ever heard of a trans refrigerant? I mean, we've heard of trans, all kinds of other things, right? But have you ever heard of a trans refrigerant? You know what it is? I bet you don't. I'm going to tell you. It is a hazardous industrial chemical that pretends to be a naturally occurring substance. I'll let you think about that one for a minute. Now, CO2, we talk about safety third, but safety is a big deal, especially with these systems. And we've jumped in here because we've got some components, which I'll show you. And Raghu, you're going to probably talk about our check valve safety relief products as one of the things that we've got to line up currently or not, but pressures can rise quickly when there's a loss of power. That never happens, does it? You never have a supermarket or a building or anything that loses. I mean, storms never come through and knock the power out. Power grid's perfectly reliable, right? No, it's not. If you lose power at a store that's using CO2 as a transcritical refrigerant, and all of the cooling quits, the air conditioner goes out, especially if it's summertime, you can get to that 88, 89 degree point pretty quickly. And guess what happens? Pressure goes up to, what was it, 1,070 psi? And there are pressure relief valves in the system that will relieve that pressure because you don't want things to explode. And then that has a whole host of other problems associated with it. But CO2 safety is a critical point. We make a valve that gets used as both a hand control shutoff valve and also can relieve internally. And you can see here, in the case of this evaporator, appropriately positioned ball valve safety relief valves can keep a horrible accident from occurring. And this is one of the first CO2 systems that I'm going to talk about at a very high level, very, very high level. Liquid overfeed, it's subcritical, meaning everything happens in this system below that critical point. The critical point, remember, is at the top of that pH diagram where we're going to see things go to 1,000 psi. All of this is going to, all of the operation, all the pressures that are going to exhibit by CO2 in this instance, if the system's operating, is going to be well below that threshold. And here we haven't included the whole thing in the diagram, but there would be a vapor compression system over here operating using whatever standard refrigerant would be available. Could be something like 404A. Heck, even if they wanted to go really crazy, they could have an ammonia plant over here that's actually rejecting the heat, an intermediate heat exchanger. And then over here on this side of the system, which includes the refrigerated cases where we're going to cool, chill, freeze, or condition whatever products are of concern, that's all CO2. And we're doing it without a compressor. We're pumping the CO2, liquid CO2. So we've got a receiver tank, pump, And pumps, for those of you who are not familiar with the term pump and compressor, pumps are designed to help move liquid substances through a system. Pumps and liquid, compressors and vapor. Sometimes when you're talking to technicians or people that have been in the trade a long time, they'll refer to a compressor as a pump. And that's just their vernacular. Technically, that's incorrect. But they know what they're talking about, but that's just their terminology part. Without going into a lot of detail, we're pumping liquid CO2 through this system, and we've called these evaporators. That's the heat transfer surface where we're going to interact with the product that we're going to cool or condition. Those aren't really evaporators. I mean, there's evaporation going on, but we're putting so much liquid CO2 into these heat transfer surfaces that it can't all evaporate. And from the standpoint of that, they're pretty efficient. And then we have heat that gets picked up. This goes back to this header, goes back to the receiver, and everything starts all over again. Some of the refrigerant is siphoned off, goes to this intermediate heat exchanger, and comes back as a liquid, and we pump it around again. Are we breaking yet, Raghu, or we keep going? This is one system that's currently in use to a certain degree. There are some of our products that get utilized through it because, and there are special considerations that need to be given to them. Gordon, if you see anything where I have a mistake in maximum rated pressures on any of these components, you by all means chime in. Those of you who don't know Gordon is probably more of an expert on these systems and some of these components than I am. He's just not as entertaining as I am. John Woodhouse here, who's right up here in front, who's keeping me under control, is our refrigerants expert by a long shot. He knows, he has forgotten more than I know about it. Again, not quite as entertaining as I. All right. Liquid solenoid valve have the need for special considerations to be used in these types of systems. We have provisions for that with high maximum rated pressure ratings on them. And we also have, for those of you that don't know what a maximum operating pressure differential is, they need to have that. And I invite you to go back and listen to my webinar presentation on solenoid valves, and you'll have definitions for all of those terms. Now, here is a cascade system depicted on a pH diagram. We've taken some liberties with this because the DX high side would have to be plotted on its own pH diagram for whatever refrigerant you had put in it. We've just done this for illustrative purposes. But the CO2 portion of it finds its way going through the system, picking up heat, transferring it to that intermediate heat exchanger, well below that critical, hence subcritical. Now, there's another system design that can be subcritical, CO2 in nature. It is a so-called cascade system, and this side of the system where the refrigerated cases happen to be, this is very similar in nature to any vapor compression cycle that you're going to encounter. The main difference is we've got an intermediate heat exchanger here that is an interface between the CO2 side of things and whatever other system that we've connected to it in the elaborate design that we have that ultimately rejects heat, usually to the atmosphere. Don't get caught up in the terminology. You'll see these used in some instances for low temperature applications, and you'll see the use of a lot of our products in these, and including electrically actuated, electronically controlled valves like this SCR that you see over here, which again, ooh, look at some of the ratings that are on this, 1,015 PSI. That's a lot. And here you see our catch-all, our contaminant control. I haven't elaborated on this, but whether it's CO2, propane, or a traditional refrigerant, probably the single biggest culprit besides ineptitude on why products cease to function properly is the introduction of contamination to the system. And that can be moisture, dirt, acids that could form. And quite frankly, that's why back in the 1940s, the smart guys that originally were operating our company introduced the catch-all, was because we were getting eaten alive with warranty returns on thermostatic expansion valves. And so we've depicted those in all of these systems. They're a good insurance policy. Again, solenoid valves are needed, and we've got a high pressure solenoid valve. Some of our wholesalers have adopted the use of our high pressure solenoid valves for a wide array of uses and aren't even stocking the more traditional structured valve anymore. I mean, there's some merit to that, certainly. Now, here is a depiction of both that liquid overfeed style system as well as the Cascade system for, that's in that instance where an owner wants to take their use of CO2 one step further, cover low temp applications, medium temp applications. And I'm not going to even begin to tell you that these are the only ways that these get set up. There are many variations of this. This is just some of the common ones, and they're the ones where I had slides already made. So you didn't pick up on that, did you not? Okay. So again, in every instance, this requires some type of traditional system to ultimately reject the heat. So again, that would be, we haven't shown all those details, but there would be a compressor over here and a condenser where the heat picked up here that was used to help cool or chill or freeze a product, then gets rejected by that system that's connected via this intermediate heat exchanger. But then back here, this loop looks just like that same system I'm talking about, but we've coupled it with one that has a pump. Just another variation. I haven't put you to sleep yet, have I, John? How about the other John? There's a couple of Johns here. Now, I might even get this done before lunch shows up. Transcritical. This is the last system version that I'm going to talk about because I'm really kind of getting tired. I've done a specialist class this week, and actually I told Ragu, I'm not going to do this. You need to schedule it for another time because I'm whooped. But here I am. Yes, we're having great fun, right? Is everybody learning? Anybody learned anything so far? Oh, wow. Thank you. Let's get a critical CO2. Now, Matt Sponhorst, you remember when I went over to Geneva, Switzerland for those trips because
I didn't want to go.
Yeah, well, because you didn't want to go. Yeah, and we had a small heat pump manufacturer over there that was a little bit ticked off at us, and they told me I was going over there under the pretense that I was going to help train the race people. But shoot, some of those folks were pretty smart. But I think it was because of my communication skills and my cordial personality that I worked with the intermediary, what do they call that, mediator, to help calm them down because they wanted, I'm going to use that term again, they wanted a shit ton of money from us, right? But do you remember that? You do? Because you didn't want to go? I went there. Yeah, and then you go, I ain't going back here. But one thing I learned while I was over there, I saw a lot of CO2 systems back in 2012, 2013. And I came back here and I said, we need to get ready for CO2 systems. I mean, they're doing CO2 and they're doing transcritical CO2 systems and they're doing some crazy stuff. Like they've got a traditional air-cooled condenser where there's air moving across it and they're spraying water on it. I mean, that's what we do over here at Plant 3 when the air conditioner wouldn't work. Right? I said, they're doing it. And they're not even trying to collect it because it's all evaporating before it even hits the ground. Oh, they even had them set up at Chilventa a couple of times. And I best I remember, they didn't even have a drain plan on the floor picking it up. They had some that were, I don't know, they had some false load on them and they were showing off what they could do. But transcritical CO2 systems, I was told, you would only see in environments where you wouldn't have excursions above 88 degrees Fahrenheit, or at least not very often, because that holds with it a whole host of fancy engineering gymnastics that you got to pull off. And here we've got some of that depicted. If you, and you're going to experience conditions where you're above the critical point. And we've come up with a fancy term with that because we can't get the superheated CO2 to condense there. What do we call it? Gas cooling. That's pretty fancy. I'm going to use the $10. We're going to de-superheat the gas before we can get it to condense. And it's actually kind of simple. And if I get in over my head, I'm going to rely on Gordon over here to help me out if that happens. But counting on that not being the case. But whoa, there it is. If you recall, we've talked about this kind of stuff at length. What is it? There's an evaporator, an expansion device. Over here are a couple different banks of compressors where we've got some booster compression going on here, which that's not all that unique. That gets done, not just in CO2. But what's unique about this system is the crazy stuff that's going on up here, because we don't just have a simple condenser that's ultimately rejecting heat. You want to give a guess what we have? We have a gas cooler valve, our gas cooler itself, that's rejecting the heat. And along with it goes a gas cooler. We've got a fancy tank over here that helps to separate the liquid and the vapor. And we got a flash gas bypass valve. Now, Gordon over here has been involved with designing those for years. He's forgotten more about them than I know. This is the transcritical system. And again, what's unique really from a high level perspective is these additional components that you see up here that wouldn't be in a traditional system. And that's the fancy stuff that has to go in if you're going to do transcritical. And what do I mean by that? You notice I don't have an intermediate heat exchanger over here and another system depicted. This one's doing the whole thing. So they're circulating CO2 all throughout the store or whatever application it happens to be. And that's the magic thing. And for the longest time, it was presumed that if you went into the southern realm of like our country, Florida, Texas, those kind of places, the independent Republic of Texas, where it gets above 88 degrees on occasion, it can be done. Good. Got to have these kind of devices. In a lot of instances, this gas cooler, which looks a whole lot just like a condenser, refrigerant's flowing through it. We got fans on it, but it's not condensing. It's just cooling it off. And they'll even use that trick that they learned from Plant 3 and spray water on it. That's pretty common, which is kind of unique. Now, if you have a system like this and you're using it to chill, cool, freeze product in a supermarket and you lose power to the store, oftentimes what will happen if it goes for an extended period to where this starts to heat up and it gets to that threshold where we're past, that high level pressure that we can maintain, it vents the CO2 to the atmosphere. Now, CO2 is around us all the time. We create it, it's around us, it's part of nature. So from an environmental concern, unless you want to say, well, I thought CO2 created global warming and now you're going to add some to it. Well, notwithstanding that argument, venting CO2 to the atmosphere is a whole lot different than venting R22 or R444A or something else. But what happens then, that system's down. And that also means whatever products that we're trying to cool, chill, or freeze, they're not going to last forever. If it takes 2 or 3 days to get the system back up online, there's a problem. So I know there are options to add either an emergency generator to keep this system running in the event they have that. There's also some systems that are designed just to cool the CO2 with an emergency power in case they lose that. So those are all things to take into consideration if you're going to go down this.
How do they monitor? How do they know how much charge they lost and how do they replenish it back?
Well, that's now one thing. The one good thing about this is, John, what is CO2? Is it a single constituent? All right. So it's not like these magic blends that have, oh gosh, what's the glide? CO2 doesn't have glide, I think, right? Am I right there? There's no glide with CO2. Yeah, it's sort of like, yeah, no glide. So if you lose some of it, you put however back much you have to put in. And there's probably instances where they lose quite a bit of the charge. I don't know if they lose the entire system charge, but there are procedures that the people that are putting these systems in place know how to undergo. And it is not just a simple affair. In fact, I know one of the contractors that's been doing the Aldi stores all around the Midwest. I grew up with him. He's a good guy. Glenn Newmeyer, smart fellow. He says when that happens, in answer to your question, when it used to be a power outage, say on a 404A grocery store, be it a Walmart or whoever, I send a technician out there. They spend 2 or 3 hours, systems back up running. This happens with CO2 Transcritical store. I send 2 technicians out there. They're out there 2 or 3 days. It's more complicated. That's the price you pay to be able to say, I'm making something that's retrofit proof, because we're going on the premise that the EPA doesn't come along and say, you can't use that anymore. You got to do something different. So they can design their system and rest assured that they're going to get to ride it out for an extended period of time. And they're being environmentally friendly. Now, also something that's interesting from my perspective is that Aldi's, because I use them as an example, because they've gone full tilt with this. Whether the stores in Washington, Missouri, or it's in Austin, Texas, it's CO2 in the United States. However, when it's not in the United States, and for those of you that don't know, Aldi's is a German company, they're using a lot of hydrocarbons as the refrigerant, which has its own set of complications that could. Yes.
So the flash tank looks like a receiver. They can see a receiver there.
Well, it's kind of okay. So if you bear with me, I'll get to here. There's the flash tank, and you've got the CO2 that enters up. So here's kind of a semi-traditional heat reclaim, heat exchanging device. And so you've got refrigerant that enters the gas cooler and it cools it off. And then you travel on down here, but I'm doing okay so far, right, Gordon? And then you've got a gas cooler valve, which kind of acts, I guess, in a way, kind of like a holdback valve to help control the pressure in the gas cooler. And now you've got refrigerant that enters the flash tank, and it's with the pressures being just right, being cooled off, you start having a combination of both liquid and vapor. So we're using that to be able to introduce vapor back here to the flash tank or to the flash gas bypass valve and keep things moving. It helps me to see that. So after a fashion, I almost look at it as almost something like a separator in a way. And we don't sell those, do we? Yeah, that's not part of our, but you need it to be able to isolate liquid and vapor. I don't know. I'm sure somebody does. I don't. We've got a number of devices in here, like the flash gas bypass valve and gas cooler valve, and a number of other things. Those ball valves with the safety relief in it, and then solenoid valves. And in fact, when we went out to the Aldi store in West County, and Dean Willenbrink and Matt Wood and the very, very astute, very brilliant Pete Sponhorst went along and took incredibly good notes, we saw a lot of our products deployed. But there's a lot of our products that weren't deployed that they could be. And I'll move on here. So those are the legacy versions that Gordon's designed. I know he's got some that are going to supplement that as time goes by. And then here's that whole system again. There's a lot of stuff in this system that we don't make. I mean, we've depicted traditional oil level controls on those compressors. Our OL whatever won't work here. They're just there for illustrative purposes. So no, they're using something that's probably similar to that, but it wasn't a Trexel. It was some other electronic device. In fact, they were telling us, I thought it was bullshit for a minute that they were Bluetooth oriented. I don't know if I believe that, but they did claim that on the oil level controls. Again, we don't make. And there's probably a number of devices in here that we could consider pursuing a design project for them. But one of the things I think we got to keep this in mind going forward. This is strictly my opinion, and that's worth, $1.50 because it might get me a small coffee and quick short, maybe.
2 cents.
Yeah, just barely. The charge restriction, the use of propane in the system has danger associated with it. CO2 notwithstanding. Propane acts very much like some of our old traditional refrigerants. And from a functionality standpoint, it's wonderful, but it's flammable. And to offset that, the draconian legislators have decided, well, you can only use so much of it. And initially, it was 150 grams. Does anybody know what 150 grams looks like with respect to a pound? Pound? Well, 454 grams is a pound. And your average 2-ton air conditioning system at home might have 6 or 7 pounds of refrigerant. So 150 grams doesn't get a whole lot done. I mean, we could run that refrigerator back there in my training room with it, but yeah, that's not a bunch. That's not much. Now, some interesting design things have been done, true manufacturing in our backyard. That's all they use anymore. And the limits, John, are they going up to 300 grams? Is that happening?
The upcoming limits, the limit that is currently in US 60335-2-89, and that is going to be in Standard Rule 26 for commercial refrigeration, is for a closed case, 300 grams, or an open case, 500 grams, half a kilogram, 1.1 pounds.
Okay, now that has the potential of changing things, because propane is relatively inexpensive and the systems don't require all these fancy engineering gymnastics over here to make work, but it is flammable. And so that has that trickiness associated with it. And over 10 years ago, there's a HEB supermarket, and that's a giant supermarket chain down in Texas, installed a store in Austin, Texas. Pretty good sized store, at least as big, if not bigger than our Schnucks, probably double the size of that. And the entire store is refrigerated with propane. They got some special dispensation from the eco-terrorists known as EPA to extend the 150 grams. And they reject heat with a combined circulatory loop of water and glycol that rejects heat through a fluid cooler, much like we do here in our building for air conditioning. And each one of the systems was self-contained, meaning it had its own compressor, its own evaporator, its own expansion valve, and an intermediate heat exchanger to reject the heat. They did that throughout the whole store, and that's over 10 years ago. And they showed that it could be done. So my only thought is, I'm leaving you with here, is as supermarkets of the future are here now, and we're going to see, we need to be prepared to try to take advantage of opportunities with CO2, but we need to be entering all of this with our eyes open and realize that there are other things that have the potential to offset that, and flammable refrigerants might very well be one of them, just to keep it in perspective. Because I think going forward, it's not going to get any better. I mean, I'm not surprised. I think there's going to come a time, if it's not naturally occurring, or at least so-called naturally occurring, as the guise of a trans refrigerant, we're not going to get to use it. And that means, things like ammonia, things like propane, things like, I think I'm about to run out of steam here. And unless you've got questions, I'm not going to answer any more things that you have to say to me. And lunch is here. You're supposed to fly out.